Where to start? I suppose it's something that happens to everyone who watches the sky, who pays attention to the universe eventually. We all, at some point, see a UFO. For me, it was about 10 years ago. I was standing on a Sussex beach, watching the sun go down, looking at a crescent moon, hoping to see the planet Mercury. Mercury is the hardest of the naked eye planets to see. I like to check it's still there occasionally. There's enough of the I Spy, train spotter, astronomer in me that it's good to see these things. And so I was staring at the moon. I knew Mercury was a few degrees away, and there was a point of light in about the right place.
Will we ever be able to see beyond the current observable universe?
Oh, it's much worse than that. The observable universe is shrinking.
If you want to know what are my odds of winning the lottery, you come straight to probability.
Yeah.
Because probability is all about how likely or not events are to happen.
I think the chance of there being an undiscovered second species, very like humans, out there in the world today is pretty slender. However,
and these are the pictures if you haven't seen them. I mean, New York was orange. The air was orange. They said one day out in that air was like smoking a pack of cigarettes. It had the same effect on the lungs as smoking a number of cigarettes. So people who'd never smoked in their life were suddenly going to suffer some of the same health effects.
Any Further Questions is a brand new podcast from Gresham College, a place where we ask our speakers all of your questions that went unanswered following their lecture. Guests have included Ronald Hutton, Robin May, Chris Lintott, Sarah Hart, and Maggie Snowling. Any Further Questions, all episodes are available wherever you listen to your podcasts.
But it was brighter than Mercury should have been. And as I watched, it began to move in the sky. And it moved in a really surprising way. It moved sharply across the sky. It was fast, and then it took a right turn, and it zigzagged its way across the sky, looking for all the world like it was under intelligent control, that somebody was steering this thing. It's not a plane. Planes flash and don't really move like that. It's not a satellite. If you go out at night, in the first few moments of twilight these days, we're blessed with thousands of Elon Musk's satellites. We're used to seeing those, but they move smoothly across the sky. This thing was not doing that. And somewhere in the back of my head as I watch this thing, you're just thinking, well, could it be? It's certainly, to me, an unidentified and flying object. But luckily, it passed overhead, and I could see it was nothing more than a Chinese lantern, a paper lantern with a candle underneath that had been blown by the wind. But if it hadn't come overhead, I would have been convinced, I think, that I'd seen something unnatural in the sky. And it's a very human thing. Ever since we've been looking at the sky, almost every culture that has an astronomical tradition talks about thinking about life amongst the stars. And so whenever we look and see anything, it's natural to question whether it might be a sign of intelligence. And in the lectures that I've already given this year, I've mentioned several examples. I talked about maps like this made in the 19th century of the planet Mars, where people conscientiously used the largest telescopes available in the world to record a set of canals that the intelligent Martians were building to move water from the poles down to the dusty deserts of the equator. No such straight lines, no such canals exist, but people saw what they wanted to see. In more recent times, we've sent robots to Mars, robot geologists that have explored the surface, and the internet has had great joy with pictures like this one from the Spirit rover, which shows, depending on your point of view, either a rock or a tiny little Bigfoot on Mars. You can raise the objection that Bigfoot's quite large, but of course Martian big feet might be a slight big feet. Yeah, we'll go with big feet. Might be slightly different sized. And so, it's hard to look at that and not see a figure, but I promise it's just a rock. People do this professionally as well. Almost every phenomenon that has been found in 20th and 21st century astrophysics has been accompanied by a set of people who think that possibly this might be aliens. My favorite example involves the detection of what are called gamma ray bursts. This is an image of the sky in high energy radiation, and the dot in the center is a sudden burst of gamma rays. These are seen coming from the distant universe, and so they appear all over the sky. They were detected first by satellites which had been sent into orbit to monitor for nuclear weapons testing, but instead discovered a cosmic phenomenon of gamma ray bursts all over the sky. What could be causing these dramatic high-energy explosions? Well, clearly, they are the signs of spaceships accelerating faster than the speed of light, because if you watch Star Trek, when the Enterprise goes into warp speed, there's that blue flash, which of course looks like this. You do need a bit of imagination to get from here to here, but still. And there were papers published in the literature that speculated and talked about how we might test this idea. I gave a whole lecture to this thing, to Oumuamua. This is the artist's impression, the first asteroid to come through the solar system, which is a fascinating interstellar asteroid to come through the solar system. This is a fascinating and interesting object in its own right, but it looked to several people, to many people, like something that could be an alien reconnaissance spacecraft. And we've even fooled ourselves. I'm a big fan of this thing, this moving object, which was found about 20 years ago, in a suspicious orbit around the Earth, the kind of orbit that you'd expect a surveillance craft sent by some distant civilization to keep an eye on us and perhaps to find out whether we've grown up yet or not. This thing, which is in the catalogue as J002E3, turns out to be the third stage, the upper stage of the Apollo 12 rocket that took the astronauts to the moon. We'd lost track of it since the early 70s and had rediscovered it and classified it as a potentially alien visitor. And so I do want to start by acknowledging that this habit of thinking about intelligence in the cosmos is both common and I think actually quite productive. It makes sense when we find something new to question whether there's intelligence out there. But, and I don't want to disappoint those of you who've queued for a while, I am going to say that we have no definitive evidence that shows us that there's intelligence out there. We're still looking. And so what we're actually dealing with is an absence of signs of aliens in the cosmos. And that's confusing. And it's become more confusing recently because we've got very good at finding homes for aliens out amongst the stars. We now know that planets are common. They're so common that the discovery of new exoplanets, planets around other stars, is now commonplace. So in the last week, we found 4 more. I can tell you about them. They've got great names. I'll deal with the second 3 first. You'll all be familiar, I'm sure, with KMT 2023 BLG 0416LB, which is a new Jupiter-mass planet around a nearby star in the Milky Way, and its other 2 companions found by the same survey. The first thing to say about this is that we better hope there aren't aliens from KMT 2023 BLG 0416LB who care about branding. It's a bit of a mouthful, and I imagine they call their planet something like Earth rather than this catalogue number. Actually, it's a sign of how common discovering planets is that we now give them just catalogue numbers. The one I was excited about this week was HIP 39017, and I'm excited about this one because we can actually see it. So these images at the bottom from a telescope in Hawaii show, well, they almost exactly don't show a nearby bright star. They're images with an instrument called a coronagraph, which hides the light from the star. It creates a fake eclipse. And so the little yellow blobs in the middle have been added back in to show you where the star would be. But what you can see next to them with the arrow pointing to it is a large planet. It's about 20 times the mass of Jupiter. It's about as big as a planet can get before it starts to feel a bit like a star. But we can actually see this thing against the glare of the planet using these special instruments. And these are always special because I think there's something really exciting about seeing another world. My favorite example, HR8799, these are images from a similar instrument, this time on the European Very Large Telescope. For those who don't know, astronomers are terrible at naming things. You sort of got that from the exoplanets. But the Very Large Telescope does what it says on the tin. We're building the Extremely Large Telescope, which will do a better job of this. We were unsuccessful in getting funding for a project called OWL, which was the Overwhelmingly Large Telescope. But we're getting to extremely, and that's good. Anyway, this is from the Very Large Telescope. And again, the light from the star has been removed. And what you can see here are 4 planets around this star. And what's nice about this is it's been studied for many years, so we can animate and show you in real images, this isn't a computer simulation, planets in orbit around a star. And what I like about this is that in almost every talk I've ever given, and every TV program I've worked on, and every time you've encountered astronomers talking about the solar system, you've seen a computer-generated animated version of this with planets whizzing around a star. But this is real data. And I think it's beautiful and exciting. The system's interesting. It's sort of like a blown-up version of our solar system. So there are 4 outer planets here, just like we have Jupiter, Saturn, Uranus, and Neptune. These are all about 2 to 3 times the size, or at least the mass of the ones that we have in our solar system. And the orbits are about 2 to 3 times larger as well. So that outermost planet on the left, making its stately way around its star, orbits in about 460 years for a complete orbit. The innermost one whizzes round in just 45 years. And so, we can see some of these planets. We believe that they're real. Most of the time, we can't do that. Not because the planets are faint, but because the glare from the star is too bright. It's like watching that Chinese lantern with its candle that I saw drift in front of a stadium floodlight and be able to pick out the candle. It's just too difficult. And so what we have to do is use indirect methods of detecting planets. And like so much of modern astronomy, and so much of the astronomy that I love, this is about making simple measurements really precisely. And so I can show you an example using our own star, twice a century, last time in 2012, next time about 100 years hence, Venus passes in front of the sun as seen from Earth. This is a video of the last such event seen from Oxford. There's Venus transiting across the face of the sun. These transits used to be really useful. People used them to scope out the size of the solar system, and in the 18th and 19th centuries, expeditions were organized to go and observe these. Cook's voyage to what turned out to be Australia was organized to see such a transit of Venus from Tahiti. These days, they're curiosities, but we can do a simple experiment. So on the right is sort of if you've got the nice video on the left, on the right we've got the lab physicist's view of the event. This is the result of holding a light meter out in the parks in Oxford. And what you can see, I love astronomy, it's such a simple thing. When Venus is in front of the sun appears slightly dimmer. If you block part of a light source out, it gets slightly dimmer, right? It's not rocket science. And it's not by much, it's by less than 1/10%, because Venus doesn't block much of the sun. But if we were in such a position as to observe such a transit, such a dip every time Venus got in front of the sun, then you'd be able to deduce that there was a planet there, you'd be able to work out the size of the planet from how quickly the dip happens, and you'd be able to work out the orbital period, how long it takes Venus to go round. Of course, you'd have to be lucky. You have to be exactly in line with the orbit of Venus so that you get this every time. Twice every century or so doesn't really cut it. But we do get lucky occasionally. There is, for example, a nearby star called Teegarden star, which is about 12 light years away. And it has at least 2 planets which happen to orbit in a plane such that they go in front of the star as we're looking at it. What's fun about Teegarden star, and here's a visualization of it, is that from their planets, they see us going in front of the sun. So if they're using the same technology that we're using, if there are aliens on this star, they will have found our solar system by now. And so if I had to bet on where the nearest aliens who know about us are, it's Teegarden star. Now, what's nice about this transit method, there are lots of other ways of finding planets too that I'm not going to go into this evening, but what's nice about this transit method is that you can look at lots of stars at once. And if you do that, you just have to wait and be lucky and hope that some of them will blink. So we've had dedicated space missions that have done this. The most famous of them was a NASA satellite called Kepler that stared at one patch of sky, just in the constellation of Cygnus, just above the horizon if we went outside at the end of this lecture, looked at one patch of sky for 3 years, monitoring the brightness of a couple of 100,000 stars with a precision that's enough to detect a tiny planet going in front of the star. And because of the results from Kepler and others, what we found is a remarkable diversity of worlds out in the Milky Way. So one way of thinking about this is to make a graph. Each dot here is a Kepler planet, or one found by another means. On the y-axis, you've got the size. So the higher up you are, the larger or more massive you are. Jupiter's at the top, Neptune's in the middle, Earth's at the bottom. And then there's the orbital period. So planets over here are whizzing around their star in just a matter of days. Further out, they're going more slowly. And of course, you could work out where the Earth was on this diagram. It would be about 365 days and 1 Earth mass. So we're down here in the bottom right. But what's clear from this diagram already is that we have all sorts of planets. We have things that we didn't expect. We have, for example, in the top left, hot Jupiters. These are great. They're easy to find, it turns out. These are as big as Jupiter, but they orbit their star in just a few days or weeks. We don't have such a thing. In our solar system, the planets that cluster close to the sun are small, rocky things. There are solar systems out there where there's a hot Jupiter or a Saturn whizzing around the star. We didn't expect that. In the bottom left, there's an exotic set of worlds called the lava worlds. These are rocky planets who are so close to their suns that their surface must be molten. They're at temperatures of maybe 1,000 degrees. We didn't expect these either. How did they form? How did they get there? Are they stable? Will they keep existing? We don't know the answers to any of those questions at the minute. I was just talking to somebody this afternoon who's doing laboratory experiments where they're heating up rock and trying to observe it to try and work out what these things are made of. In between, we found plenty of Earth-sized planets, rocky planets. We found some Neptunes, and actually the most common type of planet lies in between those two categories. It's a type that we don't have in our solar system. It's either a super Earth or a puny Neptune, whichever you like. I guess super Earth is the better branding, but 2 to 3 times the size of the Earth, and possibly, but most likely, gaseous. But we don't have anything like that in our solar system. So we found this variety of worlds, but particularly if I show you not this schematic diagram, I'm going to plot the real data, same axes, but this is all the planets that we found as of last week. So there are 4 missing. I didn't add them in, sorry. We'll do that for you at home. But you can go to actually, if you go to NASA's Exoplanet Archive, then every week they tell you what we've discovered, and they'll give you updated versions of this. So you can just keep updating this talk week after week. But what won't change, at least in the near future, is that there's this bottom right of this diagram that isn't populated. All the planets we found are up in the top left. They're either very close to their stars, or they're very massive. And that shouldn't be too surprising because those are the easy ones to find. If you're a massive planet and you get in front of your star, then you create a big dip. It's easy to see that that's happening. Smaller planets, it's harder to see. If you whiz around your star every few days, then I don't need to look at that star for very long to see many dips, to get good evidence that there's really a planet there. But if I want a planet in an Earth-like orbit, then I have to wait year after year after year to get even a single dip. And so Kepler, for example, which stared at that patch of sky for 3 years, if it was very lucky, looking at Earth, would have only had 3 dips. And it's very hard to pick out the signal from a small planet in that region. So we're not yet at the point where we're finding planets like our own. We believe that they're there, but we haven't yet managed to find lots of them via these methods. Now, we do have some tools in our armory to try and fix this. One, which is quite surprising, is that we can ask for your help. So my team in a project called Zooniverse that I ran until very recently built a project called Planet Hunters. This is led by Nora Eisner, who's currently at the Flatiron Institute in New York, where we take data not from Kepler these days, but from NASA's latest Planet Hunter, TESS, which looks at bright stars, and puts it online and invites you to look at graphs for fun. But if you're willing to do that, and you're one of the people who spots a dip, you can be the discoverer of a new planet. And about once a month, we get to send an email out to people that says, we think you found a planet. which is really exciting. And Planet Hunters is good at finding, our volunteers are good at finding longer period planets, planets that take longer to go around their star, because they're the kind of planet that you see when you inspect the data visually. When you look at the graph, you see that dip, and you're able to pick it out, whereas our automated algorithms rely on repeated transits. I can say more about that in the questions if you like. Planet Hunters have found some unexpected things as well. My favorite system is the K2138 system, which was found by volunteers on the Zooniverse. There are 5 planets in the system, B, C, D, E, and F, and luckily they're in that order, so that makes things nice. Thank you for laughing. But what's really exciting about this, well, the first thing to say about the system is that it's crammed. So Mercury on this diagram would be out here. So these are 5 planets that are very close to their parent star. The best analogy in our solar system is something like the moons of Jupiter, which are crammed close to Jupiter, rather than a solar system that we're used to thinking of. But the other thing is that there's a relationship between the orbits of these planets. So for every 3 times B goes round, C completes 2 orbits. For every 3 orbits C completes, D completes 2 orbits. For every 3 orbits D completes, E goes round twice. For every 3 times E goes round the star, F goes round twice. There's a 3 to 2, 3 to 2, 3 to 2, 3 to 2 relationship. This has consequences. One is that we can have some fun making music with this. So my friend Matt Russo in Toronto likes to turn planetary systems into music. And so every time a planet completes an orbit, it chimes, and the pitch of the chime is related to the size of the orbit. And all I want you to hear is that that's musical. It sounds nice to us. I'll defer to Milt for reasons why. But it's musical because of this 3 to 2, 3 to 2, 3 to 2 ratio. That ratio also tells us that these planets have formed and migrated together. We don't think they formed this close to the star. They must have formed further out and moved inwards. And we think that they must have done so together. Otherwise, why have they ended up in this ratio? So people are still studying the system. It was unexpected, and the complex pattern of dips that resulted were identified by the Planet Hunters volunteers, by the Zooniverse volunteers. But really, the system I want to talk about tonight is very different. It was also found by Planet Hunters. It's a star called KIC 8462852. As you'll hear in a second, I know you know it. You'll hear in a second it gained some other names. And it was observed for the whole 3 years of the Kepler mission. So this is the most exciting graph of the night, by the way. This isn't one of those astronomy lectures where you get beautiful pictures. It's mostly graphs this evening, but that's okay. This is the brightness of that star over time. And look at the whole 3 years. And you can see that just after Kepler started observing KIC 8462852, there was a dip. Quite a big one, actually. So maybe that's a large planet. It's particularly exciting that the dip reappears, but then there's no third dip. Not at the same depth, anyway. And so whatever's causing those dips, it's not a planet. Planets don't go round once and then twice and then take a break or go on holiday. That's not how this works. And so maybe this is some behavior of the star. Maybe these are big star spots, just like the sun has sunspots. Who knows? We're not sure. No one was paying a huge amount of attention until about a year later, the star did this. It dimmed. See, it is a good graph. It dimmed by about 20% for about 5 days and then came all the way back up to full brightness. And then it carried on like nothing had happened. And stars don't do this. No other star in the 200,000 that were in the main Kepler catalogue ever did anything like this in the 3 years that we studied it. The volunteers on Planet Hunters found this, they kept an eye on it, and they were the first to notice when about a year and a half later the star did this, which makes no sense. It's like somebody's got hold of a dimmer switch and has started fiddling with this thing. This earned the star the nickname the WTF star, which I think makes sense. But the volunteers, particularly Darrell LaCourse, who led a lot of this work, started thinking about what might be causing this. It's clearly not an ordinary planet getting in front of the star. And the theory that Darrell came up with was presented here on a post on the forums in the Planet Hunters website, was that maybe there's a planet with a disk of material around it. Maybe think Saturn's rings, but larger, maybe made out of dust grains, astronomical dust being carbon and silicon grains around the planet. Then when that moves over the star, it would create these complex dips of the kind that we're seeing. It's a good idea. My favorite thing about this, though, is not that the theory's good, it was, but I love Darrell's last sentence, which is, the true situation is probably nothing like this, but it seemed a good opportunity to rampantly speculate in paint. And there's a man who's understood what doing science is really about. I think that's really exciting. So, we have a mystery. We have this bizarre behavior, and we have a theory from Darrell that maybe this star is orbited by a planet with a dust disk. Dust, sand grains, carbon, silicon grains, they should get warm in the star's light. They should glow in infrared light. So if this theory is right, if there's enough dust to block 20% of the star's light, we should see it shine brightly in the infrared. So we looked, and the star's perfectly normal in the infrared. There's no excess at all. So there's no large dust disk. We started to rack our brains to work out what else could be going on. We got a bit desperate, if I'm honest. This is all work led by my colleague Tabby Boyajian, who's now at LSU, Louisiana State. But we were trying everything. We thought for a long while this must be something that's gone wrong with the camera or the data or the software. We looked at neighboring stars. None of them showed anything like this behavior. We got as far, there was an awful week where we tried to work out which pixel of the camera the starlight had been falling on every time this observation was made, because we thought maybe there was a dead pixel somewhere that was causing this problem. It wasn't that. We eventually gave up, and we sent a paper to the journal describing the WTF star and saying that we thought it was interesting, but we didn't know what it was. We got a response from the journal with a positive report saying that they would publish it, but with 2 comments. The first one was that the editor politely pointed out that all acronyms have to be spelt out in full. So WTF stands for Where's the Flux? And I should point out, lots of these people are citizen scientists and volunteers who led a lot of this work. So we solved that one. But the second problem was bigger, which was that the editor said that we couldn't publish a paper that just said we'd found a weird star. We needed an explanation. So we tried to make one up. And we eventually came up with the idea that we were going to blame the whole thing on comets. Now, comets are well understood. These are icy bodies that go on elliptical orbits in our solar system. Presumably other solar systems have them as well. In fact, we have actually seen some exocomets since. And comets misbehave. There's a famous example of what's called Biela's comet, which was very famous in the 19th century because its orbit crossed that of the Earth. And there was a panic in the early 19th century, mostly led by articles in the New York Times for some reason, that when the Earth passed through the comet's orbit, there would be a miasma on Earth and we'd all get sick from comet gas. This doesn't happen. We're safe from comets. But Biela itself suffered. This is a drawing of it made in its 1846 apparition when it appeared in the inner solar system and then split into 2 pieces. These are icy bodies that get heated up every time they come near the sun, and so they eventually disintegrate. Biela, after 1846, didn't reappear. When it was next expected, we got instead a meteor shower of bits of comet burning up in the atmosphere. So comets can disintegrate. So we thought, okay, so what's happened around the WTF star, also known as Boyajian star by this point, said, okay, there's a comet, and the comet has split up into lots of little bits. Here's an unconvincing press release image to convince you that this is plausible. And then what happens is you can arrange these comet bits to cause these dips. So we have a medium-sized bit, and then a medium-sized bit, then a gap, then a big bit, and then there's a whole host of them at the end. And we can explain our observations. I don't know, does that sound convincing? So somebody said yes, so that's good. I shall stop the talk here. What's nice about this idea, one feature of this theory, of course, is that I can explain any pattern at all just by rearranging my bits of comet. But at least it's an explanation, and comets don't glow because they're icy, they don't glow brightly in the infrared, so we can get away with adding comets to the system without violating what we knew from observations. So we published this paper, we said it's probably comets, and roughly every astronomer in the world who works on comets wrote to us. Pointed out that we do actually know something about comets. We have in fact landed on a comet. Here's the Philae probe from the European Space Agency, which bounced along the surface of comet Churyumov-Gerasimenko as part of the Rosetta mission a few years ago. Philae didn't come to a good end. It sort of ended up on its side, as you can see, but the orbiter, the Rosetta orbiter, told us a lot about the nucleus. And one of the things we found out was that Churyumov-Gerasimenko, a fairly typical comet, is about 4 kilometers across. Here's a graphic of it menacing London for scale. Not a real photo, I should say. But comets are a few kilometers across. To block out 20% of the star's light, one piece of our putative comet would have to be 10,000 times larger than the largest comet ever seen. Ice also breaks up when you expose it to heat, so we needed the largest comet ever suspected to have just broken up just before we started looking at it with a spacecraft. And because only 1 in 200,000 stars showed this behavior, this needed to be a rare event that we just happened to capture. It sounded really implausible. And we were never hugely committed to our comet theory anyway, he says now. And so what happened was other people started putting forward their own ideas about what this star was up to. And the paper that got the most attention, and I wouldn't normally in a lecture show a paper title and abstract, it's a bit lazy as a speaker, but to show you it's a real paper published in the Astrophysical Journal. This is a paper from Jason Wright at Penn State and friends, and the title is The Jihad Search for Extraterrestrial Civilizations with Large Energy Supplies, paper 4. I'm going to assume you've all read papers 1 to 3. The signatures and information content of transiting megastructures. Now, I find out about this paper when my phone rang in the office on a Monday morning. I picked it up, and a voice at the other end said, "Hello, I'm a journalist. I hear you found aliens." Now, I'm not good on Monday mornings, especially not before coffee, and genuinely I said, "I don't know, I'll check my email and I'll get back to you," and I hung up. And I sort of stood there going, what's happened now? And what had happened was this paper had been released. And the argument is quite simple. The argument is that we've long expected sensible alien civilizations to need carbon-free electricity, right? You need as much power as possible. And the source of power is the star at the center of your solar system, but it's a waste allowing that starlight to have to hit the Earth or whichever planet you're from. And so what you do is you build an orbiting swarm of solar panels. This is sometimes called a Dyson swarm or a Dyson sphere, after the astronomer who publicized the idea. It actually goes back to the 1930s with the slightly crazy sci-fi philosopher Olaf Stapledon in his book Star Maker talked about a vision of orbiting solar panels. And so Jason and co are proposing that this star harbors such a civilization, that there are orbiting solar panels, and that's what's blocking out the light from the star. So where we see a dip, it's because one of these panels has gone in front of the star. So, do we think this is a good hypothesis? It was certainly popular. It got written up all over the place. I'm going to show you The Independent because they were the only people who used the word may. Everyone else almost everyone else confidently reported that we had found aliens. One paper, who shall remain nameless, said something like astronomers in cover-up of alien discovery, which, given that the papers were all online, seemed particularly unfair. But is this a good idea? Well, it suffers from the same problem as the comet hypothesis. I can arrange my alien solar panels however I like, right? I can explain any pattern with this idea. But yet, it is an explanation that works for what we were seeing. And so I think the fair way to put it was that the best evidence we had for alien life in the universe was this star and its strange behavior. Given that that was true, we felt it important to try and test this idea. We did that by keeping an eye on the star, but while we were doing that, other people were interested enough to start looking at this star's behavior in the archives. And there's a remarkable project at the Harvard College Library which has taken these glass plates. Old-style photography in astronomy was to take these large glass plates, put them at the focus point of the telescope, usually ride along with them as the telescope moved around the sky, swapping them out every hour or so. And these are pictures of the sky taken for most of the 20th century by lots of the world's largest observatories. And at Harvard, they've been scanned and digitized, and the brightness of objects in those plates has been carefully measured and calibrated. And when they looked at data for this particular star, they discovered something really unusual. This is also an exciting graph. This is brightness over time. The blue points are the thing that matter. And this is from 1890 to 1990. So this is 100 years worth of data. And what we see is that the star is fading over time. It actually drops by about 30% over the course of a century. So now we've got two mysteries. What's causing the star to fade over time? And why does it have these sudden dips when we look at them more recently? Obviously, the aliens are constructing more solar panels. We can actually predict when they'll finish. It's in about 5,000 years' time when they will have completely covered the star. And you can speculate, if you're in that sort of mood, on how long it must be between general elections on this alien planet if they can get this sort of thing done. Scarily close to things I'm not allowed to say because of my BBC contract. So let's move on. So there's now two mysteries. I think this is a bit of a hole in the alien theory, because the idea that we'd catch this grand infrastructure project just at the point where it's being built seems implausible. It's like the fact that we needed the comet to have just broken up. But we kept an eye on the star. We used robotic telescopes around the world. This one's on the island of Maui in Hawaii. And in 2017, suddenly the star dipped again in brightness. And this time we caught it and we were ready, and we used advanced technology to alert the astronomers of the world to this event. This is Tabby telling the world that Boyajian's star is dipping. This is not a drill. Astro tweets on telescopes in the next 48 hours. Spectra, please. And genuinely, this is how science is done. We had about 200 telescopes, amateur and professional, respond to this call for observations. And they produced between them a critical piece of information, which we didn't know before, which is that we had telescopes with cameras that were set up to detect red light. We had telescopes with cameras that were set up to detect blue light. And both sets saw this dip in brightness. But the blue light dipped more than the red light. So in other words, how much of a dip there was depended on the color that you were looking at. And that means that this is, whatever's blocking the light, it's not a solid object, because a solid object would block all wavelengths equally. So we're back to sort of ideas about a cloud of dust, and we can rule out, sadly, solar panels from an alien civilization. You could have solar panels from an alien civilization with Christmas lights on the back if you want, but you have to make the Christmas lights really bright, and then you have several other questions to answer. So what explains all of this? What are our best ideas as to what's going on with this star? Well, it's still a topic of some debate, and people are still watching, but I have a favorite theory which explains both the long-term dimming and the sudden dips. And it's actually quite a disquieting and upsetting one. So we think of our solar system as stable. We're used to the idea that the planets are in their orbits. They've been there, well, not quite forever, but for 4 billion years. And we expect, there's a cheerful future of astronomy thing where I tell you that in 4 billion years' time, the sun will blow up to a red giant and will engulf the Earth. But that's 4 billion years' time, right? We don't have to worry about that now. Except that we've recently learned that stars eat planets sometimes. There was a result a month ago that showed, with this unconvincing press illustration, which is the theme of the talk, that 1 in a dozen stars shows evidence of planetary ingestion. So this is actually quite a clever experiment. They looked at pairs of stars that were born together. So these are double stars in orbit around each other. And we assume that they formed in the same conditions, out of the same material. So these stars should be made of the same stuff. And then what the team did was they looked to see if there were any differences in the makeup of the atmospheres of the two stars. And they found that in about 1 in 12 cases, one of the stars essentially had planets smeared all over its face. It had heavy elements in the atmosphere that looked rather like the remnants of having eaten a rocky planet. So this happens. How does this help us with Boyajian star, with the WTF star? Well, It turns out the theory says that when a star consumes a planet, the star gets brighter for about 1,000 years and fades slowly. So we could be catching our star in the act of fading. And if the planet was disrupted, as the unconvincing illustration shows, before being swallowed by the star, there could be rubble left in orbit around the star, and the rubble could be causing the sudden dips. So we can explain both things with this one explanation. Now, there's a catch, which is, and we were only working on this yesterday, so this might be wrong, but this is a study of double stars here that were born together. That's how you do it's a twin study, basically. You're trying to see whether one's eaten something that the other one hasn't. But there's a reason to believe that double stars would be more likely to consume planets. If you've got two stars in orbit around each other, as they travel around the galaxy, it's quite plausible that their orbits would be disrupted by an encounter with another star or passage through a spiral arm. And if you send one star on a suddenly unstable orbit, then the planets around both of them are going to get disrupted. So around a single star like a sun, our planets might be okay. Around a double star, this kind of thing should happen. So I predict that Boyajian star, the WTF star, should be a double. But I don't think we've ever looked. So we now need to go and do that. And I'll get back to you. But this planet eating is quite a good explanation. And it leaves us, sadly, with a lack of aliens. In fact, I was going to update the title of the talk. We started with "Is it aliens?" But the astronomy creed is "It's never aliens." But Gresham said that wouldn't be quite so exciting. And also, it's a bit too pessimistic, I think, because this search for this WTF star caused a lot of attention to be paid. And we found other stars that misbehave. This is the current favorite. This is 2 years of data for a star called HD 139139, which has 80 separate dips at seemingly random times over the 2 years it was originally studied. This isn't a planetary system. You can't, I think somebody worked out you need about 30 planets crammed in, all in exactly the right orbits to cause this. That's not what's going on here. You wouldn't have a stable system. And we don't know, to date, why this is happening. It's a wonderful quote from Andrew Vandenberg, who's an exoplanet astronomer and rival of the Planet Hunters team, but a friendly one, who drew attention to this star. He said, he was quoted in New Scientist talking about this discovery. He'd had the phone call that said, maybe you've discovered aliens. And he said, well, in astronomy we have a long history of not understanding something, thinking it's aliens, and later on finding it's something else. So the odds are pretty good that it's another one of those. But we're in the process here where the best explanation we've got is, yes, alien solar panels. We have done some follow-up. The Green Bank telescope in West Virginia has listened in to see if there are any signals coming from a civilization around the star. No luck. More mysteriously, the European Space Agency's Cheops satellite recently took a look at this star for a few weeks and showed no dips at all. It seems to be behaving exactly like a normal star. Now, it's possible we didn't look for long enough. There's about a 1 in 20 chance that we were just unlucky. But it may be that the star has changed behavior. So we might be learning something about how stars behave. We may perhaps be finding unusual signals that will, in the long term, turn into something important in understanding intelligence in the universe. And the broader message here, I think, is that we're used to thinking about discovering life in the universe as one of two things. Either we detect biology. There are people working hard on understanding the atmospheres of these planets around other stars, such that when we look at them with that extremely large telescope that we're building, maybe we'll be able to see in the atmosphere that there's oxygen there that on Earth would be produced by life, or perhaps carbon dioxide from a technological civilization, or one of the many other chemicals that might be what we call a biomarker, a chemical that's produced mostly by life. It's challenging because you have to understand the chemistry of the atmosphere extremely well. Or we're used to thinking about the kind of thing the GBT was doing, which is radio astronomy, the search for extraterrestrial intelligence by expecting to see a deliberately beamed signal into space, a message either for us or intercepted on its way to somewhere else. And we can still do both of those things, but I think what we've learned from studying Boyajian star and the WTF star is that we can think much more broadly about how to find life in the universe. We can start to think of looking for what are called techno-signatures, the effect that life and intelligent civilizations have on their surroundings. I want to give you a silly example, a sensible example, and a speculative example. The silly example is this. This is the Tesla Roadster launched into space by space billionaire and world's largest ego, Elon Musk, to show off his SpaceX capabilities. This car is now heading out into the outer solar system. It was reported as going to Mars. It's not. It's just shooting out into space. This, I guess, is a techno-signature. If you were an alien studying the solar system in the far future, finding this would presumably give you some idea that there was at least some sign of intelligence on one of the planets, though you might want to steer clear. We can turn that around. Would we recognize this car as something unusual? Well, it turns out we've done this experiment, and the answer is yes. There's a telescope called WISE that spends its time monitoring the sky looking for asteroids. And it has a camera that has the ability, when you find an asteroid, it tells us what color it is. And there are a couple of ways of measuring color. One roughly measures how red it is, and one roughly measures how blue it is. And you can make a plot of all asteroids using this WISE data and put these things on the axes. So every dot here is an asteroid, and where it is on this diagram tells you what color it is. And what you can see is there are three main types of asteroid, and then the red dot at the bottom is the car. It's a different color from everything else in the solar system. So we would notice that we had a space roadster heading our way. We're thinking about doing this on a grand scale just to check that there aren't alien spacecraft in the solar system. We haven't found any yet. We can think more broadly about this as we look into space. I'm a big fan of a study by Duncan Forgan and colleagues that used, I think, some quite ingenious logic. They said, a bit like Jason's prediction that alien civilizations would build solar panels orbiting their star, Duncan and co. said, well, look, one of the things you do as you moved into space, as you became a spacefaring civilization, is probably, if you've got a handy asteroid belt, as we do between Mars and Jupiter, we'd mine the asteroid belt for raw materials, for rocket parts, for rare minerals that we can't get on Earth. This is something that's being talked about now. There's a whole fascinating side conversation to have about the economics, but people have talked about going and getting rare earth minerals or platinum or even ice from the asteroid belt. And the logic is that where you have mining, you create dust, inevitably. And so what we should do is look for star systems that have a suspicious glow in the infrared coming from an excess of small dust grains in the system, because that's a sign that there's been active mining. And there was nothing very suspicious, but people have started to look for these things. Maybe we can detect the side effects of alien mining. And I said I'd give you a speculative example as well. I was at a conference about the future of looking for extraterrestrial intelligence. And it was a very sober and serious discussion about machine learning and anomaly detection and the techniques that one would use to do this. And I nipped to the loo and came back a few minutes later, and the conversation had changed, and people were talking about whether alien intelligences would be pleased by the notion of making stars in different bits of the galaxy flash in different patterns. Sounds crazy, but we could check for that. We could look for unusual patterns amongst the stars, and maybe that's how we'll discover there's life out there. We have a new data set coming. We have a telescope called the Vera Rubin Observatory, which is as big as the biggest telescopes today, but which will scan the whole sky every 3 nights, producing 30 terabytes of data a night and about 10 million alerts a night that something has changed. And in there, we hope, will be all sorts of things. There'll be stars misbehaving, perhaps flashing in unison. We'll have a catalogue of a few million objects in our solar system that we can search for unusual orbits, or perhaps even the odd shiny metallic thing that shouldn't be there. We'll detect more interstellar visitors, and we'll look in detail at distant galaxies. And what's becoming clear is that as well as searching that data and using it to do conventional astronomy, it's worth spending some time thinking about the most profound question of all: is it aliens? Thank you very much.
Thank you so much, Chris. I should announce that Chris will be signing his latest book, Our Accidental Universe, outside after this talk.
Yes, this is the first Gresham lecture since this book has been out, so I promise this is the last time I will advertise it. But if you'd like to hear more stories like this, then please come and get a book. Right, that's the advertising done.
So we have lots of questions. I'll start with the more sensible ones, and we'll get to all of them.
I've just seen your T-shirt.
Oh,
I forgot
yes.
to have a go at Pluto. Sorry,
Yes.
yeah.
Okay, so let's go with this one. Are the fluctuations of the, careful how I say this, WTF star similar to the dimming of Betelgeuse a couple of years ago?
That's a great question. Yeah, people will remember perhaps in 2020, actually the end of 2019 into 2020, Betelgeuse, the bright star in the top left of Orion, which is a familiar presence in the winter sky, dimmed quite dramatically. I found it. You may remember 2020 was an odd year. I found it really unsettling that Orion looked different. If you went out and looked up, it didn't look like it was supposed to. No, what happened there was Betelgeuse is a red giant star. It produces dust in its atmosphere. And so we could see that happening with the VLT. So that took months to play out, whereas these are much more rapid changes. So they must have a different, and this isn't a red giant, so they must have a different origin. But it's a good question.
Is the James Webb Telescope going to help in finding exoplanets, Chris? Tell us.
Yeah, so the JWST, which is our new infrared telescope, probably won't discover exoplanets. Actually, apparently I'm doing all my plugs. On next month's Sky at Night, I've just recorded an interview with Beth Biller, who's using JWST to do some direct imaging, so you will actually see the planets, but it won't be discovery. What it does is follow up and tell us about the planet's atmospheres. And we're heading towards a world in which you can look at an atmosphere and say something about its chemistry. But for JWST, only for planets that are close to their star. We'll need bigger telescopes to do better.
Okay, I won't respond because there's so many questions here, so we'll just get through.
We'll do rapid fire mode.
Okay, are there any correlations between the types of exoplanets and the type age predisposition to eat planets of the stars they orbit?
Yes, we don't know yet because we've really only, this is the double star study I talked about was the first systematic study I've seen on whether stars eat planets commonly. It was something we need to look into more. I find it quite disturbing. There have been these hints for a while that the solar system may have been unusually stable, that other planetary systems are unstable, maybe atonal music and all sorts of things if we're visualizing or sonifying their orbit. So don't know, watch this space.
How do the stars actually eat the planets? How do they catch them? Is it usually only one of the twin stars that is a planet muncher?
Yeah, this is a great question. So yeah, there weren't any in the study where both seem to have eaten a planet. So in these systems, the stars are far enough apart that they likely both have their own solar systems. There are worlds we've discovered which have two stars close together and planets going around both of them, but they're a separate story. So what's happening, we think, is that either some gravitational interaction between the planets causes one or more of them to fall into the star, or some disruption to the whole system maybe causes one of the stars to swing by on its orbit and disrupt the planetary system of another. So the dynamics of this are quite predicting exactly what's going to happen is quite complicated, but showing that this kind of thing could happen seems quite easy. So things are much more fragile than they seem.
Does it have something to do with the stability, the 3/2 nature of it?
Oh, yeah. So the 3/2 is interesting. The 3/2 ratio may be more stable. So because they've settled into a relationship with each other.
So you get punished for making a bad
That's right.
chord.
So they're not going to disrupt each other because they're in this nice pattern. Whereas we think early in the solar system's history, I mentioned this in a previous talk, we think Jupiter and Saturn got into a resonance where their mutual gravitational interaction meant that they were suddenly dramatically moved. So Jupiter seems to have come inwards, Saturn seems to have gone outwards, Uranus and Neptune may have swapped places. But we thought that was something that happened to a young solar system, and then everything was supposed to settle down into a nice middle age. It seems to be that may not be the case.
Is it possible that the changes in brightness are due to solar mass ejections or solar flares?
Yeah, this is a great question. So we see the sun change brightness. So the sun has sunspots, which cause it to dim. though not in this sort of way. And we have solar flares or coronal mass ejections which send material out into the solar system. We do see with Kepler and with TESS, these satellites, we do see flares, but they're brightenings. Things get brighter. And this particular star doesn't seem to ever do that. It only dims and then comes back to its previous brightness.
Well, we have a hypothesis here.
Good.
Suppose WTF planet aliens required high-energy blue light.
Right.
So build a Dyson sphere to capture blue light to minimize the mass. The sphere's translucent sails, obviously.
Yes, the trouble is we have thought about this, and obviously you can make alien technology do whatever you like. So with the caveat that magic alien technology is not allowed, anything that's absorbing starlight should heat up. Things that are hot grow in the infrared or the red. So we think even if you had some magic technology that could only absorb the blue light, you would radiate away in the red as well, and we'd still see it. So we think that we can get away with arguing against that, but
the challenge with extraterrestrials is that we don't have any to have an Occam's razor to work with.
Yeah, and I gave a version of this talk to some of the schools groups that we work with Gresham this afternoon, and one of them said, look, why are you assuming that aliens do things that we would think were sensible? And that's a really good question. I don't have a good answer to that. So yeah, so this is why I mean that quite seriously. Magical alien technology can do everything you want. So you can explain the apparent lack of aliens by cloaking devices, which work perfectly. Great, good, done. We can now all go to the pub. So we can only really work within the realms of the physics that we're thinking about. But I still think that gets you a reasonable way into thinking about what techno-signatures you should look for.
What I want to ask you is, for 20 years ago, there were more UFOs seen by people, and also there's been a close shave of where a UFO has landed and it's been seen by a police officer in the United States, and somebody got off and then went back into this disk-like object and disappeared. Are you rejecting these sort of things as complete fallacies, or is there some truth in that?
Yeah, I think it depends on my mood, frankly. One answer is that I'm an astronomer. So I want to point out, before I say anything else, that I have expertise in images of space and how telescopes and cameras built to do that work. And so I can say with certainty that we don't see any evidence of such technology beyond the atmosphere. One can invent cloaking devices and all sorts of technology, but if there were things zipping around the solar system, we would have seen them. Now, as for the reports, and these days they tend to go under the phrase UAP, because it's considered a more unidentified aerial phenomenon, I believe. It's a polite version of UFO. There are lots of reports which have been much in the news recently. I'm no expert on airborne cameras and so on, but to me, given the surveillance technology that we have, given the images we have of both Earth and space, and indeed on the ground, I would be deeply suspicious of a phenomenon where the only ways it turns up are in blurry pictures or the occasional recollection. So I would think that if such things were common, we would have much better evidence. And so that's the polite way of saying that I don't give much credence to such reports. But I certainly understand, as I started by saying, the desire to want to have aliens here and to talk to them. I think that's a very natural and human thing. It's not surprising that when people see the unusual or the unexpected, or they experience the unusual and unexpected, that that's the reach that they go to. And hopefully that's a polite and sensible answer. But thank you for the question.
However, from Chloe, age 11, if there were aliens, what do you think they would look like or be like?
Well, this is a really good question. So I've got two answers. One is, I have no idea, right? We can't imagine. Look at the variety of life on Earth. If you look at creatures from the deep sea.
But it's carbon-based.
Yeah. But even within the constraints of life on Earth, where everything is DNA-based, everything is carbon-based, and we share a chemistry, look at the variety that we have. So that's one answer. So who knows? And certainly I think we could be guilty of limiting our imaginations by Star Trek budgets, right? There's a reason that all aliens in science fiction are about 6 foot tall and humanoid, because it's cheaper, right? So I wouldn't want to say for sure. However, you could make an argument, and this is an argument due to a guy called Simon Conway Morris, who's a paleontologist, who says, look, we're a good solution to intelligent life, being about this tall, having bipedal limbs, having 2 eyes, is a good way of encountering the kind of planet that we find ourselves on. So he argues, based on looking at evolution on Earth, that if there are intelligent aliens, they will look roughly like us. So the answer is go wild and speculate, or they'll look exactly like us. And I think either end of that extreme is a good answer. But
Great. Is there another question in the room?
We are often saying these days that we're at a point where the first person who's going to set foot on Mars is alive right now. Do you think we'll ever realistically get to the point where we are going to be able to definitively visit or communicate with one of these exoplanets? Or do you think we just have to be satisfied with just knowing all the questions but not having the answers? Or do we just wait for them to contact us
yes,
first?
there is the waiting option. I have a friend who, I think as a joke, but I'm not really sure, runs the WETI Institute, which argues that because the aliens are clearly more intelligent than us, instead of searching for them, we should just wait for them, so that's WETI. And, there are days when that appeals. No, but you're right, we think we've got this cosmic speed limit. So even Teegarden's star is 12 light years away. So even if there were aliens there, they knew about us, we knew about them, and we were exchanging radio messages, you have to wait 12 years for a reply. Even the nearest star is a few light years away. Travel, even at 99% of the speed of light, is going to take you years and years to get there. So there's a boring physicist's answer, which is conversation will be very slow. I still think it would be fascinating to know that there was a world there with life on, but we may have to restrict ourselves to very slow conversation. However, every time a physicist has predicted what we'll be able to do in 200 years' time, we've been wrong. And so I'm looking forward to the invention of the Lintott drive in the next 50 years, which will take us at interstellar speeds, and then we can explore the galaxy. But if we can do that, I want to know why we don't see people doing it already. Why are we not watching the starship zip around space? Maybe they're hard to see, maybe it's physically just very difficult. So I fear that Einstein's right and we have a cosmic speed limit, but I hope that we'll be able to beat it.
Okay, let's go back to a very solid technical question. In measuring the light dip from a planetary transit, how do you adjust for changes in cloud cover?
Oh, well, this is a great question. So that's one reason I probably didn't make this clear enough. Kepler and TESS are in space precisely because it's a lot easier, because then you don't have to worry about the Earth. Now, you can do it from the ground. There are projects that have discovered transiting planets from the ground. But what you have to do is observe for long enough that you see transit after transit after transit after transit, so you can build up evidence that something's happening despite what's happening with cloud cover or even just changing conditions above your heads, even from clear night to clear night. So going into space is the best way, and that's what we've started to do.
Have we looked from a long way away at what we look like using these various methods?
Yeah, people have simulated it. We haven't actually done so. So as I said, Teegarden's star, people have looked at what they'd be able to discover, and we think that Mercury, Venus, Earth, and Mars would be obvious, and Jupiter and Saturn would be harder because they take longer to go around. Some of the nicest things with this has been where we've used spacecraft that are flying past the Earth to study the Earth in exactly this way. So the most famous example of this was the Ulysses spacecraft, which went past on its way into an orbit that studied the sun from above. And they didn't have a camera on board, but they looked at what they could detect of the Earth's atmosphere. And the conclusion of the study was that they'd found life on Earth, but they weren't sure whether it was intelligent, which I think is rather nice.
Okay, we'll do one last one from online and then maybe one last from the floor.
Okay.
Is it possible the orbit partner of the star is a small black hole, occasionally eating away at the star's mass?
Yeah, black holes seem to get invoked. They're almost like aliens in that almost any astronomical mystery you can invoke a black hole. I think you would see the evidence, if it was close enough to disrupt a planetary system, I think you'd see the star wobble. And we've got spectra of it. We don't see it moving around the black hole. So I think we can rule that out. Of course, you could have a very small black hole, but then it's probably not a useful one. So yeah, I think we can rule that out because the star doesn't appear to be in orbit around a massive thing.
Great. Okay, so the last of the evening, let's see what it is.
Yes, this will probably suffer the same fate as the comets, but if one imagined just a mass of rubble, maybe a solar system that's exploded and cooled down, and this is transiting sort of across between us and that planet, would that not accommodate these various dips in the brightness?
Yeah, that was something, that's a really good idea, and it's something that people consider both in orbit around the distant star, like the star, but also maybe in between us and the star, so you've sort of got rubble just in the way. If it's around the star, it should be heated, and like the comets, it would glow in the infrared, so I'm afraid we can rule that out. But it's a really good idea, and we actually see such things around other stars. They're called debris disks, and they seem to be the outcome of some periods of planet formation, leaves rubble all over the place. So we've actually seen that, but in this case, I don't think that's what's going on. But yeah, no, you've invented something that exists in the universe, which I think is all we can ask for as astronomers. So thank you. I think that's really, really good.
Thank you so much to Professor Chris Lintott for a wonderful lecture. Thank you for coming.